Now, when we're talking about atoms, we do know that it is the number of protons that dictate, what it is. And what it is it's going to be a substance, and actually it's going to be an elemental substance. So if we take some atoms, say maybe some carbon-12, 6, and we join a whole bunch of them together, and just one, then we form this elemental substance, also known as the elements. And so kind of picture a block, and you join enough atoms together to get something that we can actually touch. And suppose it's all carbon, then we're going to have a block of carbon. If it's all iron, we're going to have a block of iron. And to date, there are 118 that are known. The lightest and most abundant is hydrogen, and then it goes to helium and so on and so forth. And roughly 92 are going to occur in nature. The other ones, the extra 30 or 40 or so, they're pretty unstable, and so we can make them in the lab, but they tend to disintegrate fairly quickly. Words like atom and element can pretty much be used interchangeably. Now, chemists have gone and taken all of these elements, again defined by the number of protons in an atom, and they've kind of lined them up in a periodic table where you can kind of think of it as a roadmap of the US, or a roadmap of elements, and essentially it's kind of arranged by atomic number. And what the atomic number is dictated by, the number of protons in the nucleus. And as we work our way left to right, there's going to be one more proton and generally one more electron than the preceding element. And on the far right, the outer orbits, or the outer shells for the electrons, are filled to capacity, and these are known as the noble gases. And what this means is these guys generally don't like to play with other elements, because elements join together by sharing electrons, and these guys are kind of greedy. Their outer shells are full, fat, and happy. So just a quick little preview of the periodic table. So here we can work our way from left to right, so left to right, and here we have the most abundant one, hydrogen, kind of given that symbol H. And this number right here is the number of protons, and this is the atomic mass number. So you kind of pop our way over here, and you see, okay, well, this guy has 2 protons, and it's got an atomic mass number of 4, so it's got 2 protons and 2 neutrons, and we call this guy helium. And we kind of work our way, if we add one more proton, we call this lithium, and it's got an atomic mass number as such. And kind of work our way, 4, 5, 6, 7, 8, 9, 10. And again, these guys right here, all of their outermost orbits are filled to the capacity with electrons, and they just don't like to play with each other. So just a little bit of practice. If we know the number of protons that an atom has is 44, it has an atomic number of 44, and a mass number of 100, then how many neutrons does it have? Hoping that you guessed 56. Why? Because 44 plus 56 is going to give us 100, and to get the atomic mass number, that's going to be the number of protons plus the number of neutrons. Now let's kind of come back and take a look at the sizes of the atoms, and again, this is dictated by the outermost electron shell. And really, as we stack more and more and more electrons into an atom, then what we're doing is we're increasing the charge in the outermost shell, and what that's kind of doing is that's tending to shrink some of the inner orbits. Now, what the sizes kind of look like is that's going to be hydrogen. This is going to be helium. Helium is going to be a little bit smaller because we've stacked some more charge in there. And then we're going to jump up in size to lithium because we've jumped up to the next electron shell. And then it's going to get smaller as we stack more charge in there. And then we're going to jump up to having 3 electron shells or orbits, and then we're going to get smaller. And then we're going to jump up to the next number of shells, smaller, next number of shells, smaller. Now let's just get a little bit more terminology out of the way. You may have seen this in chemistry. Ions and isotopes, these are kind of different flavors of atoms. An ion is simply going to be a charged atom. And it turns out that we always necessarily have to have the same number of positive charges and negative charges. And if we have a deficiency of electrons, so suppose I have 2 protons and got my electron orbit out here, and I'm missing an electron, so there's a deficiency of electrons. Well, look, positive, positive, negative. So overall this is going to be a net positive ion. And if for some reason I had 3 negative charges, so 1, 2, and 3, then look at that, positive, positive, but 3 negatives, 1, 2, and 3. So negative ions are going to have an excess of electrons. If we talk about isotopes, now that's going to be an atom that is the same element as another element, but it's going to have a different number of neutrons. So if we thought about having maybe something with 2 protons, and now I'm actually going to draw the neutrons, 2 neutrons, then that's going to be essentially helium. And if I were to add a 3rd neutron, I'm not changing the number of protons, so I'm not changing the element, I'm just kind of tacking on an additional neutron. We'll simply call that an isotope, and its behavior is identical. It is a little bit heavier though. So how do we write ions and isotopes? Well, kind of coming back to the slide where we talked about atomic mass number, how the atomic number is related to the number of protons, and atomic mass number is the sum of protons plus neutrons. If we wanted to write a positive ion of carbon, it's going to have 6 protons, it's going to have 6 neutrons, and it's only going to have 5 electrons. Then the atomic mass number is going to be 12, right? 6 plus 6. So we're going to write 12 right here, we're going to write a 6 right there, and we're going to make this guy a distinct positive. And if this was for some reason a negative ion, if it had 7 electrons, then we would say it's going to be 12, 6, and a minus sign right there. Now, another isotope of carbon is going to have 6 protons and 7 neutrons, so these guys are different now. You add those guys together, and you're going to get an atomic mass number of 13. So this is going to be carbon 13, atomic mass number, number of protons. Just want to make sure you're staying awake. The atomic number is going to match the number of protons in a nucleus. Now let's get a little bit more jargon out of the way, compounds and mixtures. If we have atoms of different elements and they chemically bond to one another, then they make what's called a compound, and it's going to look and taste and smell very, 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 very different than the elements from which it was made. Because it's not pure, we're not calling it an element anymore, and pretty much we can only separate it by chemical means. Example is going to be salt, or NaCl, and the chemists kind of care about what's going on, and they'll talk about covalent bonds and stuff like that. I know that they're sharing electrons and stuff like that, but I really don't care too much about it. What I do care about is when you have some sodium and you have some chlorine and they join together, then it's going to release energy. In order to pull this guy apart, then it's going to take energy. So I always like to think of magnets. If you have a magnet right here and a magnet right there, when they join together, that you're going to hear a click. That means energy is released. It takes energy to physically pull these guys apart. I care a lot more about the energy than the chemistry. Now, if we do have some atoms and we mix them together and there's no chemical bonding or anything like that, then we simply call that a mixture. For example, air. Air is going to be a mixture of nitrogen, oxygen, methane, and several other gases. And these guys don't have any chemical bonds, they're just all kind of mixed together in the same pot. Now, molecules are like compounds in that it's 2 or more atoms bonded together. Compounds that had to be different elements are molecules. It can be the same element, and they work pretty much the same way. There's chemical bonds in between them, releases energy when these guys join together. It takes energy to pull these guys apart. So for example, you could have ammonia, NH3. So that's going to be 1 nitrogen atom with 3 hydrogen atoms bonded together on it. You could have methane, which is going to be CH4, 1 carbon, 4 hydrogens. You could have H2O, you can have water, which is going to be 2 hydrogens and 1 oxygen. Looks a lot like Mickey Mouse. Or you could have something like O2, it's going to be a molecule, and it's going to look and taste and smell very, very different than just a single oxygen element. Now, we can rearrange these atoms and molecules, and generally that takes some energy. It takes a chemical reaction. What I care about is where is the energy. And think to magnets. If we were to pull molecules apart, it's going to take energy. Pulling magnets apart takes energy. If you combine atoms, if you have two really strong magnets and you hold them in your hand and they join together, then you're going to hear a click, and that's going to be releasing energy.